All right, so quickly, what we're going to do, we're going to spend some time looking at the ideas, going through some math problems that we're going to be expecting on the test. Okay, look at and study those ideas. This is Mr. Chung here. He's just observing today. You can say hello. If you want to know more about him, he's an electrical engineer. Okay, he's an electrical engineer with his PhD in electrical engineering. So feel free to talk to him at some point if you'd like to. Not during class though. Are you going to be here later in the day, or what time are you here today? From 1 to 1:30, we have lunch. These guys are all in there. So if you want to, a few of them are going to electrical engineering next year. So it'd be nice to talk to these guys. I'll let you know. So in the lunch room at 1 o'clock. All right. So first thing. Heat transfer. Remember, people, with heat transfer, you're only transferring from hot to cold, right? You're only transferring hot to cold. So if you have two surfaces, even if you have ice on one surface and the desk on the other, or considered to be the other, the heat is going from hot to cold. So the ice is absorbing the heat from the desk. You can never transfer the other way. The idea of heat transfer is one direction. Okay, again, whatever is hotter, that temperature gradient that you see, the difference in temperatures is what you're really important, or what you really should be thinking about. So the first thing we want to write is when you have delta T, a difference in temperatures, okay, you have heat transfer. And always, always, always from hot over to cold. Now, if you have two surfaces that are the same temperature, what do we call that, everybody? Equilibrium. When two surfaces are at the same temperature, they're not going to want to change any heat because they're already balanced out. So if there's no heat transfer, delta T is what? Zero. There is no difference in the temperatures. Okay, so again, when delta T equals 0, you have a state of thermal equilibrium.
He said the word.
Okay, remember, there was force equilibrium. When two bodies are or one body is undergoing two forces that are balanced, like me right now, my weight and the normal force. That's force equilibrium. There's also moment equilibrium, which is rotational. Right now we're looking at thermal equilibrium. Okay? Again, when delta T is 0. So when two objects are the same temperature. Right now, this room is not the same temperature as what it wants to be. So for example, the thermostat is set at 72. Because it's not 72, it's going to want to change the temperature of the room until it gets to that state. And what that is called is like a controlled system. You want the system to eventually settle out. So you want it to asymptotically become closer and closer. So the temperature of the room might be at like 80, right? Then it turns the air conditioner on to get it down to 72. But then it shoots below 72. So then what does it do? It kind of turns the heat on, or just turns the air conditioner off for now, right? So then it comes back. And then eventually it'll settle out. Just like when you hit a speed bump, remember? When you hit a speed bump, what happens? You start to fluctuate, and then the springs in the damper system eventually cause you to get to an equilibrium state. So that's what's happening there. Same idea, heat transfer, okay? So just to know real applications for your test. All right, let's look at now some example problems. Okay, some sample ideas. Let's go into a phase change. Okay, let's start with the hardest one that we did was our phase changes. So let's say we've got H2O, okay, which again, H2O can take three forms: ice, water, and steam, even though they're all H2O. So remember, we're not calling it water right now, just H2O is easier. If you have H2O at negative 25 degrees Celsius and is going from negative 25 to say positive 40, okay, at negative 25, what is it called? A solid, good, a solid. Everybody, at 40, what is it called? Liquid or water. How come you know this, Christian? Good job, Christian. Because 0 is my what? Your phase change. Good, your phase change location. So it's a freezing point, or we can call it the melting point, or we can call it the what do you call it? Fusion. Very good. Remember, vaporization. Heat of vaporization is between liquid and gas, whereas fusion is between solid and liquid. The direction of the phase change does not matter. It's still called vaporization or fusion. Now, remember, if it's going from a solid to a liquid, it's melting though. It's going from a liquid back to a solid, it's solidifying, or it's freezing. Okay? All right, so here, how many parts of this problem do you have to think about? 3. What's the first part? From where to where?
From negative 25 to 0.
Second part?
Phase change. And then from 0 to 40.
Very good. Well done, sir. Okay, again, we're going from 25 Celsius to 0. Then we have a phase change that undergoes at 0. Then we go from 0 up to 40. So when we look at our formulas for heat transfer here, we think of Q equals MC delta T for my temperature change, and then Q equals ML for my phase change. Again, MC delta T and ML. So here, we're going to need our table. Okay, say again? Degrees Celsius, yes, degrees Celsius, degrees Celsius. Okay, I put it for one of them, I assumed you knew it was the second. So we've got Q equals MC delta T for this portion, and Q equals MC delta T over here. Well, what should I do? Thank you. Let's give them subscripts. Okay, I'm going to have to know how much mass there is. We'll leave it in terms of F for this problem. But if you had a mass, we can plug it in. What is the C value again? What does it mean though?
Specific heat.
Good, the specific heat, whatever is given. Now, are they different or are they the same? Remember, different states actually have different specific heat capacities, and water is one of the few that you notice there is a very significant, I was going to say non-negligible, but significant change. Okay, double negative. So here, call this C1, call this C2 now. The mass is not changing, it's a controlled system. Remember guys, if you were doing this in real life though, and you were doing something that vaporizes or evaporation, you would change mass, wouldn't you? Because this container that's not really closed. But in a closed container, or a closed system, the mass is not changing, it's a constant. In the middle, what's my formula? ML. And what is an L? L of what? Good, fusion. If it was not fusion, it was the other is? Vaporization. There's a little V there. Okay, a little V. Now, just to give you guys a little preview, of what your formula sheet will look like, so you can see.
Shows test. There you go. There we go. No, I can't memorize it.
All right. So here's what your formula sheet's going to look like for this test, because you need tables. So first, we're going to have our temperatures. Okay. Again, this stuff you could memorize, but it's always available on the data table, so you don't need to memorize it again. Think about this like a reference table. Okay. If you know C, then you can know F. If you know F, you know C. Remember, Fahrenheit, Celsius. The difference between Kelvin and Celsius is 273 and 0.15. Don't worry about it for now, but keep in mind, if you're doing real scientific experiments, these decimal values, they do matter. Okay, they do matter. If you're looking at a problem and it says round to the nearest degree, you don't need this, obviously, because it's the nearest degree. It would be negligible. If you're doing a multiple... Guys, come on, listen. Stop the undertone. If you're doing a problem where it's multiple choice and it's rounded, then obviously round, okay? So think about it when the problem comes up. It'll say. Now, this is Q equals MC delta T, Q equals ML. I'm not putting F and V. You need to know there. Next. These were the formulas we looked at for conduction, convection, and radiation. Okay, and I'll explain more of those when we get to that topic in the review. Now, the important thing we're going to look at right now is our data tables. So, we are looking at H2O. We need to know its specific heat capacity as a solid and as a liquid. As a solid, we call it what again? Ice. So here's ice. As a liquid, we call it? Water. Here's water. And take a look. The values are significantly different. This value here, water, looking like, I can't even read that from here, 4.186 is approximately double the specific heat capacity of ice. Okay, so they are very different values. The other thing you want to know is your L value. Take here. This is all given, what I'm showing you right now, okay? All given. So for water, we're looking at latent heat of fusion. We see that our temperature is 0, which is what Christian had memorized, so it's given, so you know that you're passing a phase. And we take a look at our value here. Remember the units on these, okay? Because in the end, when you're solving for energy, what are the energy units? Joules. Your energy units are joules. And that's why you see joules per kilogram. Because your formula for this part is ml. And mass is in kilograms, and joules and latent heat is in joules per kilogram. Kilograms cancel, you're left with joules. Dimensional analysis to check your work. So for this problem, I'm going to need to use these numbers now. All right? So somebody please write them down quickly before I go to the next page because it's going to go away. 209, 10 to the third. 4186, 10 to the third. And then 3.33, 10 to the fifth. Remember, guys, latent heat of fusion is always less than the latent heat of vaporization. It takes more energy to go from a liquid to a gas. That comes up right here. This is where it shows it to you. It takes less energy to go from your solid to your liquid. Okay, again, this is always going to be less than this one.
That's 4.1.
That's 4.186 times 10 to the third. This is 3.33 times 10 to the fifth. Okay? So when we go through this example, let's continue. Yes, thank you. We got the recording set up. Now, the mass was not given, so this problem might say leave it in terms of n. Leave your answer in terms of n. What does that mean again? There's no m, so there's an m in your answer. There's an m in your answer. Be careful. It only cancels out if you had a problem where something else had a mass in it and it would drop off. But in this case, there's an m in everything, so you're going to start by factoring the m out. So there'll be an m in the answer at the end. Julie?
So this is for phase changes, right?
For phase changes, yes sir, phase changes.
They're all multiplied by
Okay. So we got the C value for the first one was 2.
0909.
And remember, my units here, joules per kilogram Kelvin. Now, I use Kelvin here. What is our temperature in though? Celsius. But if I'm looking at delta T, what's my change in delta T here? Positive, right? And I know that Celsius and Kelvin have the same increments. So I can just call this 25 Kelvin here. Again, delta T is really my final minus my initial, which is really positive 25 Celsius. But Celsius and Kelvin have the same thickness in a sense. Their increments, their values, their delta X's or delta T's for each temperature are the same. So here, we're just going to simply put 25 kelvins. And take a look at your answer. Make sure it makes sense. Watch. Kelvin, Kelvin. This would be kilograms, wouldn't it? And this would cancel with this, wouldn't it?
Yeah.
So you'd be left with just joules. Okay, just joules. But keep in mind, we're solving in terms of n. So this right here is only the first part. The second part, I factored out the mass already. See that m that factored out there? I took the m from all three of these and factored it out. So what's left in the middle term? Just the latent heat. And my units are joules per kg, per kilogram.
Why do you add here instead of multiply?
Because if you go back to your formula, remember, we're trying to find the total heat transfer. And in class we said total heat transfer is the sum of all the heat transfers.
Okay.
So in this formula, when we look at it, I didn't put it here, I should have, I thank you. Put a plus in each spot.
Yeah, so that's why I asked before, is they're multiplying and they're adding.
Sorry, again, if you want to know the total heat transfer, we talked about it in class, you want to find each stage and then add them up. The net or sum of the heat transfers. Remember we just said sum of? It was just this? Okay, that was what we said in class. You have many heat transfers from one of them to 3, 4, 5, however many of them there are. All right, that's the second part. The third part. I have a mass, right? But what did I do with all the masses already? I already factored them out. So this mass, this mass, this mass, they all went out in front. So all that's left now is C delta T. What was the C value there? 4.1. There's my C value. What was my change in temperature in this last part? 40. Again, go back, please. Look at the problem. 0 to 40. Final minus initial. 40 minus 0. 0. And I'm going to put kelvins here. Now, at the very end, what should I do around this whole thing? Good. A bracket or a big parentheses, because my mass is going to be multiplying the sum of all those values. So in the end, for a multiple choice like this, you get that number, the number that you would get there, and then multiply that by m. So if you got, I know this is not the answer, but say that all turned out to be a number like 500,000. It would just be 500,000 m in your answer. If you're given the mass, you simply multiply by the mass. Again, the mass is a constant. It's not changing. Okay, it's not going to change at all.
So that's specified.
So we could do that instead of pulling M out of everyone.
You could, wait, say again? We did pull them out of everything.
Yeah, but.
What could you do instead? You could technically just multiply them if you know for sure. Okay? Yeah. You could, if you know M, you can just plug M in every spot.
I don't know which one.
Ask again.
I was saying that instead of we pulled them out because it's like one big problem,
Mhm.
we could have pulled out each one.
So could you have just put an M in each one of these and then factor afterward?
Yeah.
Sure, same difference, yep. It'd be like star. If you have X in all these spots, 2X, 3X, and 4X, you add them up, right? Common terms? It'd be the same thing. They'd all be like terms. All right.
So whatever you get, like once you get that you multiply that by the mass?
Correct. So if you were given a mass, you would multiply by the mass, yep. And remember, guys, whatever you ended up getting for this part, whatever you ended up getting here, the units should be joules per kilogram. Take a look. Cancel, cancel. Cancel, cancel. You're left with joules per kilogram, joules per kilogram, joules per kilogram. Because it's going to be M times whatever that number is, joules per kilogram. Because kilogram would actually cancel with kilogram in the end, leaving you behind with just joules. Okay? Just joules. All right. Let's take a look at another idea. What was the idea of temperature? What is temperature really? Average kinetic energy. So, if I have molecules and suddenly they start moving faster, what happens? The temperature goes up. Again, if I have molecules that start to move faster for some reason, and think about it logically, you start running outside, right? What happens? You start to, your body's starting to heat up. That's all what's happening. Okay, I mean, a lot of other stuff's going on chemically, but generally, your body's heating up. Let's see. Quick conversions. Quick conversion. Let's just do one example, okay? So if you're given, let's say you're given 40 degrees Fahrenheit, and in the problem you need to use it, but you have to use it in kelvins, because our problem is in kelvins. What do you have to convert to first? And then Kelvin, okay? So we go to our data table. Again, you want to get Celsius, don't you? And we said it was 40 for Fahrenheit. So 40 equals 9/5, and now you can just put a big C or TC, it doesn't matter, because we know, actually, let's use TC, because that looks like specific heat.
Minus 32.
Okay? So what do I do, Kenny, quick?
Minus 32.
Multiply by?
The reciprocal of 9/5.
Very good. So, subtract 32, you get 8, equals 9/5 TC. Multiply by the reciprocal, you're going to get 40 over 9 is equal to TC. Okay, that's going to be 4.4 repeating. Okay, so that's my temperature in Celsius. Now I want to go to Kelvin though, right?
Yeah.
How do I get that?
Plus 270.
Good. I add the absolute value, which is 273. Very good. So take that value.
4.4.
Okay, again, I'm rounding right there. If you want to put the 1.5 in, it might be useful here because now watch what happens. When you add these two decimals, it's going to round up now. Okay, it's going to round up now.
I thought you turned it Celsius. I thought it was 5 over 9.
Yes, so it's 9/5, but I have to get rid of the 9/5, right? So I got to multiply by 5/9.
Okay.
So that's why I got 40 over 9. Okay? These drop off. Now, the key point here to remember, guys, is that you have to do this in stages, okay? In stages. Now, think logically before you actually come up with an answer here. If it's 40 degrees outside, isn't that a pretty chilly day? When does it start to snow? What's the degree again, really? 32 you need to have, right? So that's at least freezing. And isn't 0 freezing for Celsius? So look at our answer, 4. That's pretty close. Because if 32 Fahrenheit is 0 Celsius, then 40 Fahrenheit should be a little more than 0 Celsius. Okay? That's why this answer is reasonable. Think about the sensibility of your answer. Say it again. If your freezing temperature outside is 32 Fahrenheit, that corresponds to 0 Celsius. So if you're at 40 Fahrenheit, which is a little bit above, your Celsius temperature needs to be a little bit above 0. That's 4.4. Okay?
I want to go back to this slide.
The other slide, which one though?
The one we just,
Unfortunately, it went away. It was on here, so it went away. Just check your neighbor real quick, okay? Yes. Yes. Remember our phase change diagram?
Yeah. You should like put one in filling in with the half.
It's like physical science. That's too easy.
You did that chemistry.
Yeah, I know, and physical science. Just so we're all familiar, here, somebody annotate or dictate what's going on, please.
Solid.
Solid, what's happening to it though?
Heating up.
Good. Solid heating up. Then a solid is changing into a liquid. Then the liquid heats up. Then the liquid changes into a gas. So you have both here. And then the gas heats up. Okay, you got to know what's going on in these diagrams. Correct. Horizontal, because there's no delta T in a phase change. Remember, my axes here, my axes are Q and T. Okay? I can add a lot of heat. The solid will warm up. Then it'll start to melt. And no change in temperature. Then it'll become a liquid, change temperature. It'll become a gas, change temperature.
Do we have to know, like, when water is, like, goes all the way to a vapor? Like the
Refrigerant cycle?
no, like a sublimation and
The term?
yeah.
We didn't really go into it, but you should know sublimation.
No, I asked.
Chemistry.
I asked. I always forget. That's why I asked.
I mean, know the word, sure, but it's not something that we really honed in on, right? We didn't look at any of those instances. All right, what about
Condensation.
our three modes of heat transfer? Let's go into them real quick. So, first, in class, guys, remember we did some of the problems we used Q dot, which was the heat flow rate, okay? But let's just analyze and write down what these are again. Conduction, and I'm not going to label these. This is convection, and we'll discuss why we know each of these. And this was my radiation. Again, your formula in class was a little different because we did Q dot, okay? Now, some key things to remember, key things to know, and we discussed this in class. For conduction, what is the important thing for conduction? There are three important things for conduction. Contact area. The more contact area you have, take your hand, put it on your desk. You can feel the heat transferring from your hand into the desk. If you take a single finger and do that, it's much less heat that's transferring, right? So because you have more area, more surface area. That's where this A comes from. Next, who can tell me what was K? It was a constant, very good, called the conductivity. Very good. Thermal, not electrical conductivity. Right? Because when electrical conductivity, you're looking at how the electrons are going to flow there. Okay, so you have rubber and metal there. Here, we're looking at thermal conductivity. And remember, thermal conductivity, everything's going to have some thermal conductivity. Even if it's very, very, very small, there will be some thermal conductivity. Does everything have an electrical conductivity? Like rubber does, but it's so negligible that no electrons flow. Okay. I wasn't sure about that. So, I know, I wasn't a good answer. That's what I'm going to talk about. I'm like, yeah, I know it, but I don't know that much. So,
you're not as smart as you.
I've told you that many times. If an object is more conductive, or if K goes up, more heat's going to flow. So remember the example of the glass windows. Why are they double paned again? Ken. I know you all answers, only one.
No, it's for the insulation area.
Thanks, Christian. So, the glass has a certain conductivity value. Let's say, I don't know what it is on the hand. Let's say it's 0.5. Then the other glass has 0.5 also. Air, though, has a very low thermal conductivity. So the air in between there is like a bit of a resistance almost. Like putting rubber between an electrical circuit to stop it from flowing. It's the exact same thing. So what we drew the other day, if you remember, the double pane glass, we drew this. We said there's going to be some heat flow. It's going to go through the thickness of the glass. Then it's going to slow down inside of the air. Then it's going to go through the glass again and come out the other side. But this is what's slowing it down. Okay? The idea of the heat flow, it hits the glass, it goes through the glass, but then it slows down in the air. Then it goes through the other glass. Okay? Because air's conductivity is less than glass. That's why they put air in between. And I don't even think it's just O2. I'm pretty sure that they actually put a certain combination of gases.
Something like argon.
Argon? Yeah, I remember being something with a very, very low thermal conductivity. Okay, and certain gases, or noble gases, have a tendency to have lower conductivities there. So argon might be between there or some other substance. But again, just going through the idea.
So they use that all buildings in like houses?
No, well, newer. If you look at old windows, if you have in your old house, you might not see a double pane. Like the house that I live in, the windows don't have double panes. It's an older house. Okay, but newer windows and stuff, you can see the other pane if you go and look from the side. Look at an angle, you'll see both panes as well.
That's a pain to change. That's a pain to change.
It's a pain to change.
I know.
Oh, I got the
All right. So again, guys, the key for double pane windows is conduction. Conduction. Okay. Double pane or just windows like that in general. What about convection? What did convection have to do with? Oh, sorry, one more thing. Sorry, one more thing. So we got K and we got A. What is this T1 minus T2?
That's change time. Change temperature.
My gradient. My temperature difference. My temperature difference or my gradient. Again, this value here is really delta T, which is the difference in temperatures. For example, the very simple example, if the temperature of one object, like, is there anything in there? Is it cold? Kind of cold. This is colder than my hand is, and there's conductivity from the metal. Okay. So what's happening right now? I'm sorry, James. I'm making it warmer because the heat is transferred from my hand, higher temperature, to the actual substance, lower temperature. Okay. Again, higher to lower temperature. So if there's a bigger temperature gap, more heat is going to transfer. If there's only a small temperature difference, much less heat will transfer. It's like taking an ice cube and putting it in boiling water. What's going to happen? It's going to melt. All the heat is going to transfer from that boiling water into the ice cube, causing it to undergo a phase change right away. A lot of heat. Increase the humidity. In cold water, it lasts for a while. In the cave. In the cave, the conductivity. Okay, guys, let's get back. Focus, come on.
19 days of summers.
Houston. Last chance. Serious, okay? The area over there, guys. You know, sometimes you're talking about other stuff. He's the one asking the question. You're all talking. Kind of rude, right? You wouldn't want people to do it with you?
When you burn out, does it work the same way?
Chemical change. Chemical change. Remember, we're talking about physical changes. When you burn something, it undergoes an irreversible chemical change. So it's not the same thing. The idea of heat transfer is still there, but it's not going to be the same thing as phase changes. Okay? All right. Next, convection. Somebody raise their hand. Tell me how convection works. How does convection work? Julian.
Convection is when
Conduction. Conduction. I know, they sound very similar, right? They sound similar. Trees. A what? Little louder, trees. Good. A fluid flow. Convection occurs when there's fluid flowing over a surface. Remember, fluid is either liquid or gas. Again, liquid or gas there. So, if you have, for example, the simplest example is evaporation. Okay, you're going to have the liquid flowing over it. You're going to have the fluid flowing over it. Okay, you're going to have a heat change. You're going to have a change in the actual evaporation so that of the substance. It's going to evaporate over time. The easier thing to think about, though, was the computer, right? What do we talk about with the computer? The fan. So you have that heat sink. We took it apart to look at that processor. You have the heat sink that sits on top of the processor. The fan is going to run over the fins. And it was more Edgar and Christian that took it apart. Oh
my God!
Okay. So, again, we had heat transfer. The air from the fan was blowing over those fins. The more fins we have, the more surface area we have. So if you look at the formula, if the surface area goes up, there's more heat transfer. And think about it logically. Okay, if I had just a block of metal and I ran some air over it, it's going to cool it off, right? But if I, instead of having a block of metal, had the same size object, but instead there were a bunch of these little fins on it. So it looked like a radiator. Okay, a bunch of different slats of metal. So you have these sheets of metal. There's a lot of surface area, right? So that heat is willing to leave much faster. Okay, the heat can exit those surfaces much faster because there's an increase in the surface area. Okay? As opposed to here, where you have just the surface on the outside. Here you have a bunch of inner surfaces. So remember, as the number of fins goes up, the area goes up, thus Q goes up. As the amount of fins goes up, the overall area goes up, therefore the Q value will also go up. Okay?
If this surface area, if this is the surface area, why is it called HA instead of SA?
Oh, sorry. H is something different. A is the area. H is our conductivity, or not our conductivity, our convection coefficient. Okay? Our convection coefficient. Julian, H is similar to K from the last example. Okay? H is similar to K. Now, what does H have to do with? H has to do with several things actually. Okay? The velocity of the fluid flowing affects the heat transfer. Okay, that can be lumped into a term like H. You can lump it in there. So for now, let's just call this the convection coefficient. And as that value goes up, like K, as that goes up, the heat transfer overall will also go up. Okay, they're directly related because they're in the numerator here. Finally, Ts minus T infinity. What did this have to do with? What was S?
The temperature surface.
Surface. What was infinity though? The environment or the ambient temperature. Okay, again, the difference between the surface and the ambient temperature around it. We're going to use that again when we get to radiation. Okay, so again, delta T. Delta T. Radiation, last one. Remember these two values. E, I said, was emissivity.
Yeah.
This sigma was the Stefan-Boltzmann constant. 5.67 times 10 to the negative 8, I think I said, was that? Right? You don't need to know the names, just know that these are constants. But this E, the epsilon actually, let's just write it down again. It's in your notes if you look. Epsilon is your emissivity. Sigma is your Stefan-Boltzmann constant. I'm just going to write the word constant for now. Okay? Stefan-Boltzmann is the name, but it's a constant. Again, a constant.
And what was the number again?
The number doesn't matter, but I think it was 5.67 times 10 to the negative 8. It's one of those random ones that I think I memorized when I was in school, but I don't remember for sure. Okay? So we're going to need those two values. Now, think of epsilon and sigma together as just another constant. Okay, think of epsilon and sigma as just a constant. Because together they make up like a K or like an H. And then after that, what do you see again? Area. So the more area you have available, the more radiation. But the big key here was the temperature. Remember this?
Yeah.
Because why? Pardon?
Related to the fourth.
Good. The difference is not just multiplied, but the difference to the fourth.
Each letter.
So the not each one, the difference. You can't distribute.
In the notes it says the surface went to the fourth and the infinity went to the fourth.
Yeah, I have that.
Yeah, you supposed to put it on top.
Check real quick. Radiation. If it's
How do you feel
Ts minus T infinity to the fourth, or it's Ts to the fourth, So, I apologize. That's my fault, guys. We all make mistakes. Relax.
Look at that. I would have
Change it, please. Change it. Now, the point makes no difference right now. The point is this. The larger temperature change gets amplified. Very good. Good use of word. Thank you. I was trying to think of the word we used in calculus, which was for a volume changing. Like, no, we talked about it as something error, propagating. So the difference here is some value, but you're raising it to the fourth. So that difference gets amplified or propagated. The error is more, or the change is more. Okay? All right. Let's see what else. What was some other stuff that we talked about? Oh, okay. What about this?
Yeah. You get 4 and 4 here.
Next.
From that homework that you did.
Say again?
From that homework you gave us so far.
Calorimetry? Sure. I want to get through two more things though beforehand because we had to study them still. So remember this formula: PV over T equals PV over T. Okay, again, this came from PV equals nRT. Okay, our ideal gas law. So what this tells me is this: if I've got a container, let's say God bless you, I've got a container to start. The container is closed. It's closed. If I were able to add heat to it, okay? If I suddenly put a heat source underneath it, we did this in the lab the other day. What happens to the pressure? It increases. It increases because, think about it mathematically. If this number goes from, say, I don't know, 20 to 50, then the pressure has to also go up from some value to a new value. So if this number increases, for this to remain a constant, this value needs to increase. So this is the formula you need to know. This is your initial, this is your final. Okay? So if you're given an example with, like, I don't know, the tires in your car. Say the tire pressure is 33 psi, but the temperature goes from 20 degrees Fahrenheit, and then suddenly the next day it's like negative 20 degrees. So the temperature went down a lot. Don't your tires get a little bit flat? Because the pressure is reducing. The pressure is going down. So you'll see that flatness in your tires in the winter. So the idea is what's really important here. That when the temperature changes, you're going to see that pressure change. Now, if I had a balloon though, if I had a balloon and I started to heat it up, it would start to what? Expand. Because my volume is no longer held constant. Okay? So my volume will go up. Is that your question actually? Make it light. How would you put it?
Yeah.
Think about a hot air balloon. A hot air balloon initially is not going to be necessarily as big as it could be. It could be deflated, right? But then you start to put heat under it, what happens to it? It starts to inflate. It'll reach its limitation, right? And then it'll start to float off.
Isn't this the one that's been in kilopascals?
Pressure is in kilopascals. Pressure. Can I borrow your pen for a second?
What? Yes and no.
I don't know, so.
What?
All right, take out your homework from calorimetry, please.
I heard my name here.
So we've got what page was it? What page? Quick. What page was the homework? Thank you, James. Sorry, thank you, Sharice. I didn't hear you.
What did you assign?
It was definitely on there.
I didn't know number. What name?
I can see which copy.
Karen, I don't know. It was when we did calorimetry, the day we did it. Look for the video titled Calorimetry. At the end, I put it on there. I also put it on Facebook and on Redline. I actually wrote the content.
I can't read it.
It's not my choice. They all changed the timeline. I didn't do it. They changed it. All pages changed the timeline. It's terrible. All right. You can change it back to regular, not timeline? How?
There's this whole process.
Okay. Maybe they'll show me after, okay? I can do that. Yeah, I agree. It's annoying. All right. Let's get back to the topic now. Your homework was to do numbers 1 through 4.
I have no idea. I think you're talking about Facebook. You're talking about Facebook?
We're not talking about any more of them. So, numbers 1 through 4 was the homework. Do we want to go over a particular one?
Yes, number 9.
Number 2? Number 2?
For a little bit after.
This is page. There we go, 316. All right, so we're going to be taking a look at number 2 now. Number 2. The problem here is giving us a sample, okay, of tin at 97.5 degrees Celsius, and it's dropped into a certain amount of water. So what's it going to do if the water is cooler than it?
It's going to give off heat.
Good. It's going to give off heat. Very good. The tin is at a temperature of 97 degrees Celsius and is dropped into water at 10 degrees Celsius. So it's going to naturally want to give off its heat. What's going to take heat? The water. The water will take the heat. If the water takes too much heat, what will happen to it? It will evaporate. It'll undergo a phase change. Okay? It's good to think about. So let's go to this problem now. So, they want to know what the final equilibrium temperature is. Who remembers, what was my formula for calorimetry? Julian. Okay, it's just Q equals Q to start, remember? Okay, Q equals Q to start. We put negative here, correct?
Yeah.
Okay. And, very good. M1C1 delta T1 equals M2C2 delta T2. What is 1 and 2? Different substances. Before it was initial and final. Before it was, okay? So we got tin and water. Now, the hard part about this problem is that you need to find a temperature, right? And a lot of people get confused. Well, let's write this out again. I'm going to write it as M1. Sorry, there's a negative there. C1. Now, here, watch what I'm going to write. T1 final minus T1 initial. Again, delta T means final minus initial.
Really?
Over here, yes, really. Over here, I'm going to put T2 final minus T2 initial. Now, this is where you need to use your intuition and your conceptual knowledge. In the long run, as time goes to infinity, as the limit goes to infinity, as this object goes on forever, what happens to them? They balance. They become what? A state of equilibrium. So, the final temperature of the tin and the water need to be what? The same. So, what are we solving for is this, here and here, and they're the same. So you don't have to call them now T1F and T2F, because they're the same. So just drop the subscripts there, and that's what you're solving for. Again, because the temperatures at the end need to be identical, just call those both T and solve for T now. You know everything else. Everything else is given to you in the whole problem. All you need to find is T now. Okay.
Why is that side?
Because remember, one of the objects is losing heat, and one of them is gaining heat. So when we do these numbers here and we subtract, one of them is going to turn out to be negative, one is a positive. But we have an overall balance of heat transfer. Okay? One is gaining, one is losing. All right, let's solve, people. Let's solve. What do I do? So which one goes on which side, though? Does water go over here or tin?
Water is gaining.
Does it really matter?
Yeah,
Think about it, guys. I know, but you got to think about this stuff. If I put this one over here and this one over here, then I'll have two negatives over here. If I do a reverse, I'll have a negative and a negative. It's still going to cancel. Okay, use common sense here. You're going to have two negatives in the end no matter what. Okay? Now, sorry, not common sense. Use deduction.
How would you say you might be able to lose? So losing.
And then associate that, but try it, start. Instead of arguing, just try it and you'll see. Okay? Now, what do I need to know? I don't need to know. You have to be honest. You know what I mean? Try it, you learn yourself. That's how you learn stuff. Try. I need to know the heat capacity of water. What's the heat capacity of water from that table before? 4.186 times 10 to the third, or 4186. Okay? The specific heat capacity of water is 4186 when it is in the liquid form. Okay, in the liquid form. The heat capacity of tin is 230. So I'm going to plug in one on one side, one on the other. I'm going to plug in the mass on one side, and I'm going to solve for T. Let's do that. So I'm going to use the left side as my water. Okay, it doesn't matter as long as you're consistent. So we have 0.115 kilograms of water, and I'm not moving the page yet because I need to read. 0.115 kilograms times, it's given, take a look, it says it's dropped into 0.115 kilograms of water, times 4186 joules per kilogram Kelvin, parentheses, T minus, what's the initial temperature of the water? 10 what? 10 Celsius, so 283 Kelvin, right? Okay, 283 Kelvin. Again, it's 10 Celsius. To get Kelvin, you add 273. So it's 283 Kelvin. Now, that's the left-hand side of the equation. Let's go to the right-hand side now. 225, 97.5. The right-hand side is going to be negative 0.225 kilograms. Okay, the right-hand side. Again, guys, come on, keep up with the problem. You should have it written down by now. It's your homework. 225 is the sample of tin. It's the mass. You need to know this. Next, the initial temperature is 97.5. That's going to go at the end. The specific heat capacity is 230. Okay, times T minus, and then my temperature. Remember, this is 97.5 what?
Wash that down.
Good one, good one, good one. Celsius, Celsius. So what am I going to do to it?
Kelvin.
Good. And 273.
15.
373, 371.15.
No, decimal matters.
I want to throw this
I did ignore the decimal there, so I'll do it here again.
No, but the different was there was a decimal in the original. You know what I mean? Because there's a decimal in the original, it would affect it. I was about to put my finger there. Calm down.
97.5, which makes it 371.5. Again, guys, I know I didn't include the 0.15 there. It's okay. All right. So for this problem, the only thing that makes this difficult is what? Okay, decimal setting up, but T is in two locations, right?
Yeah.
So you gotta solve for it. It's not a problem, just get your numbers. Okay, get a constant over here,
Get a constant over there.
distribute it, get a constant over here, distribute it, combine like terms. Okay, combine like terms. I'm gonna finish going through this one. What do you get from 4186 and 0.115? Or does somebody want to lend me a calculator?
That's all right. Wait, so your physics teacher
4186
481
times 0.115.
Is that me? Am I the only one to see something wrong?
I see a lot of things wrong with things, but I think we'll let them go for now, okay? Okay, on the right-hand side.
Negative 91.87.
Okay, that's what we end up getting here. Please, we need to distribute and combine like terms. I'm stopping here. Finish the rest on your own for this. Okay, finish the rest of that one on your own. Any general questions on the other ones that you might be confused about? Any questions on the other ones that you might be confused about? Out of 1, 2, 3, and 4. 4? What's the question? Can we do it? I can talk about it, but I'm not going to do it now. You can do it on your own. It's your homework. So number 4. Number 4 says, a hot, just minted copper coin is placed in 101 grams of water to cool. The water temperature changes by 8.39 Celsius. So if water was here, we know delta T of water already. Again, water is here. You know the delta T is 8.39. The temperature of the coin changes by 68. That will go over here, 68. So you're given this delta T as 68, given this one as 8.39. Your mass of the water is 101 grams. Convert that to kilograms to put in with your water, which was over here. Next, you know the C values. C of copper is in your table. C of water is also in your table. Your goal is to find the mass of the coin. So given C for both. Delta T for the coin goes here. Delta T for the water goes here. That's in the problem. Coin, water. Mass of the water goes here with it. Solve for the last mass that's there. Again, all of these problems are simply rearranging formulas. That's all you're doing every time. It's just to know where to put stuff, okay? So if you see that there's a temperature change, you're given delta T. Again, you are given a temperature change. When you see the word change, you think of delta. So the temperature change goes directly in here. You don't need to do TF minus TI. This quantity, delta T1, is 8.39. 101 grams of water is the mass over here. 68 is the change in temperature of the coin, given there. You're giving your C values in your table. Find the value of M2, the mass of the coin. Okay, find the value of M2. All right, before we end today, I want to quickly just reiterate who's coming today. Do you remember, or do you want to look at it real quick? For the cornstarch stuff. Do we know who's coming today? If you know you're coming today to help out, raise your hand.
We go next
I
week.
can't go anymore.
I can't go anymore.
It's my birthday.
Oh, that's fun.
Because it puts
You should have planned that, though. You knew it was a
Yeah, but it's
birthday.
fine that you forgot about it before. Right? What you said it.
It's fine you're not coming for that, but it's not fine you forgot about it. So wait, who's going today? Just two? Is that it? Are you serious? You said you were going? Who's doing the earlier shift, though? What shift were you doing? Elizabeth? I don't want you to do it by yourself, though.
You know
I really don't. I don't want one person being here. I want more than two, more than one. What's the earliest time you guys can get there today? Because the first shift was 4 to 5:30. Second shift was 5:30 to 7. You want to just do 5:30 to 7 today all together? We'll do everybody in the second shift, and then next week we'll do a full shift. Because again, I know the person put it up on the site, but not everybody knows what we're doing. So today might just be an advertisement. Okay? And what I've done is this. I've made some advertisement flyers. I've laminated them downstairs. We'll have those set up at the table, and then I'm going to have a laptop, not mine, but a school laptop there, where we can run videos on this. So we're going to run just a video, loops of the non-Newtonian fluid, and see how it works, so people can see it.
Have you asked convenience stores to donate in front of
I haven't.
No, there's some. I mean.
No, I know.
You think it would be ridiculous, but some convenience stores.
I don't think like giant would do it.
We are.
I feel like we need more of a mom and pop store that does it.
We are a poor school.
I'm going to ask the teachers all here to bring in some cornstarch, at least like a pound or two each, so that we can get, maybe like 40, 50 pounds out of them. Then we can do like 400 or so somehow. Yes, but if we're not doing the earlier shift, I'm going to just meet you guys there at 5:30 and bring everything down. Okay? So let's just do 5:30 then, because I have to be here for other stuff. So we'll all meet there at 5:30. I'll leave school around 5, go home, get the table, set it up at the farmer's market, and you guys meet me there.
Why don't you ask shoppers to one of the streets to donate? Because you know how I work here? Like they were talking about how they donated, they donated a lot of stuff because our students go to the shoppers, and we promote them basically, so they donate stuff to us.
They donated.
Who would I ask that, manager?
I don't know.
Because they donated.
What do you guys want to acquire?
Like 4 packets of water for like the.
If one of you guys would like to try this, here's what I'm going to do. The flyer and the information that I typed up for us to post at the farmer's market, I'll put that on headline and Facebook tonight. If you want to just bring a copy of that to a grocery store and ask them and say, our teacher is Mr. Howell, you can give them my email address and stuff if they're willing to donate cornstarch. By the way, it has to be local, and the other thing is, we cannot accept donations of money at the farmer's market. I talked to Mr. Martin about it. We can only accept cornstarch. Because there's no. Hopefully people will bring it next week then if we advertise today. I'm just telling you, okay? Think about why.
I understand that, but this is the after-school.
I know, guys, but there's nobody, like, for example, there's nobody that's going to be supervising you all the time. Like, I'm not going to be there at the early shift next week. And unless there's a teacher supervising, we can't just accept money. Okay, because there's no credibility. I ran it by him, he said it's not going to work, sorry. I'll run it by him again, see if maybe he'll change his mind. But I tell him that I'm there. Okay, we won't accept money if I'm not there.